In 2022, I wrote a review article on diffusiophoresis, diffusioosmosis, and microfluidics. The paper highlighted the fundamental aspects of diffusiophoresis and recent advances in microfluidic experiments on the topic. My main argument was that since diffusiophoresis is a physicochemical hydrodynamic phenomenon, it is necessary to consider the coupled interactions among particles, solutes, and fluid flow in the analysis and design of experiments. I also pointed out that there is a discrepancy between the characteristic scales of interest in diffusiophoresis theory and microfluidic experiments, so both approaches require careful attention to their blind spots. The following presentations discuss 3 original research projects that investigated these aspects of diffusiophoresis. In the first article, we studied a situation where diffusiophoretically translating particles reveal the local flow structure that disperses them. We used the Taylor dispersion analogy to obtain the best one-dimensional representation of the 3-dimensional experiments. In the second article, we studied the diffusiophoresis of charge-regulating particles along pH gradients. Through experiments and model calculations, we visualized scenarios where both surface chemistry and microfluidic flow structure must be considered. In the last article, we combined all the knowledge of diffusiophoresis, including the electrolyte and non-electrolyte models, solute-solute interactions, local flow structures, and biological elements, and identified the diffusiophoresis of microtubules along various cytoplasmic solute gradients. With experiments and theoretical analysis, we show that the occurrence of diffusiophoresis is possible in spindle assembly. I hope these results provide insights into future research directions in diffusiophoresis. In this video, I'll discuss our recent publication, Diffusioosmosis-driven dispersion of colloids, a Taylor dispersion analysis with experimental validation, with a focus on the microfluidic experimental aspect. The work is published in the Journal of Fluid Mechanics in May 2022. The main storyline of the work is about obtaining an appropriate one-dimensional equation that can describe the distribution of a particle patch undergoing diffusiophoretic translation and diffusiosmotic dispersion. We focus on the diffusiosmotically induced liquid flow in dead-end pores under a salt gradient and apply Taylor dispersion idea to include the effect of flow-driven dispersion in the effective diffusivity of a particle patch. By going through 1, 2, and 3-dimensional features of the experimental system, we motivate the need for the current theoretical approach and the experimental validation. Now let's look into the details. Diffusiophoresis is the spontaneous motion of colloidal particles under a solute concentration gradient. If a spherical particle with a negative surface potential is located under a concentration gradient of salt, there is liquid flow generated along the surface, which is called diffusiosmosis. Such a surface flow will shear the particle in the opposite direction at speed up, and the resulting motion is diffusiophoresis. The simplest form of the diffusiophoretic velocity formula for a system with a symmetric electrolyte is mobility times grad log C. Here, gamma p is the diffusiophoretic mobility for ZZ electrolyte, and C is the concentration of salt. For more detailed explanation of diffusiophoresis, please refer to the inserted video in the top right corner. Scientists have actively demonstrated diffusiophoretic migration of micron-sized particles as the typical diffusiophoretic mobility induced by a common salt gradient like sodium chloride is 1,000 times higher than the particle's Stokes-Einstein diffusivity. Since 2008, Microfluidics has become an extremely popular platform for studying diffusiophoresis of micron-sized particles. By using various channel designs, scientists were able to create steady-state or transient concentration gradient of solutes. These system designs and more detailed features of microfluidic diffusiophoresis experiments are thoroughly discussed in my recent review article. So I'll start talking about one channel design that we frequently used in our research, which is the dead-end pore configuration. The dead-end pore geometry has this typical design. Narrow pores are located at one side wall of the main channel, so that both the transient solute gradient and the corresponding particle motion can be observed along the pores. Such a configuration is known to be useful for studying one-dimensional diffusiophoresis, as the salt concentration profile is nearly one-dimensional inside the pore. In this way, we can compare the experimental results with one-dimensional solute diffusion equation and the particle advection diffusion equation. In the experiments, depending on the choice of the initial and boundary conditions, we can entrain particles into the pore along the solute gradient, compact existing particles toward dead end, or withdraw existing particles by changing the sign of the solute gradient. Here we're seeing the typical experimental videos obtained from the entrainment and compaction configurations. In these systems, negatively charged polystyrene particles in the main channel move into an initially empty pore, or the same particles that are initially located in the pore move toward the dead end by diffusiophoresis. To compare with one-dimensional transport equations, we detected the fluorescent intensity distribution at different times, and the peak location was chosen as the comparison parameter. As you can see from the comparison plots, this strategy works well, and we were able to investigate diffusiophoresis of polystyrene particles under multivalent electrolyte gradients and in the presence of varying zeta potential. So far, it appears that the dead-end pore experiments are meeting our needs by confirming the predictions of the one-dimensional model. However, the actual experimental setup is three-dimensional, and we're capturing the two-dimensional picture, which is the height-averaged view of the dead-end pore. So if we revisit the compaction experiment with a focus of individual particle level behavior, we see that although the collective behavior of particles appears almost one-dimensional, the two-dimensional effect emerges as a curved particle boundary. Such a shape tells us that the particle velocity is not uniform across the pore and suggests that there may be cases where the one-dimensional diffusiophoresis model is not enough for predicting the particle behavior. Then what is actually happening inside the pore in the presence of a one-dimensional solute gradient? The solute gradient that moves particles also generates the diffusiosmotic flow along the pore walls. In microfluidic experiments, PDMS is commonly used as the channel material, and its surface typically exhibits a negative surface potential when in contact with an aqueous phase. Therefore, the direction of wall diffusiosmosis is in the opposite direction of the polystyrene particle motion. This surface flow sets up a non-zero pressure gradient in the pore and induces bulk flow that has a parabolic velocity profile. Therefore, the effective velocity of particles is not anymore just the diffusiophoretic velocity, but the sum of diffusiophoretic velocity and the local flow velocity. As a result, the compaction boundary is not flat but instead takes on a parabolic shape. By including the two-dimensional flow effect and considering the multi-ion diffusiophoresis, we were able to predict the profile of the compaction system, which agrees well with the experimental data. Now that we have confirmed the influence of the two-dimensional flow effect as a parabolic compaction boundary, we proceed to test another configuration where an additional dimension must be included in the analysis. Now let's consider a configuration where a patch of particles is introduced at the inlet of the pore and translates along a salt gradient. To set up the salt gradient, we used 1 and 10 millimolar sodium chloride in the main channel and in the pores. We observed that when using 3 different pores with the same width and length but different heights, the particle behavior varied. In the inserted clips, you can see that the initial particle patches look almost the same in the 3 pores, but the translation and dispersion behaviors are clearly different. So at this point, an important question arises. What is a good one-dimensional representation of diffusiophoresis in a 3-dimensional dead-end pore geometry? Unlike the entrainment and compaction configurations, detecting the peak location in the intensity plots was not effective in characterizing the behavior of the particle patch. Also, the two-dimensional parabolic flow velocity cannot explain the difference among these pores because the 2D flow velocity is identical in these 3 two-dimensional videos. we created these schematics to illustrate the different layers in the pore and how the particles are distributed at different heights under the same solid gradient. In the compaction configuration, the parabolic boundary at different heights are averaged out in 2D imaging, so that the apparent boundary observed from the experiments can be nicely described by the two-dimensional simulations. However, in the particle patch configuration, the particle dispersion pattern in different Z layers is not averaged out in the imaging, but reveals the full 3D flow structure inside the pore. So obviously, the two-dimensional flow velocity cannot explain the different widening behaviors of the particle patch in the pores of different heights. So now we consider the three-dimensional flow effect. As you can see from the plot, the height averaged velocity, which is the orange curve, is similar to the two-dimensional parabolic flow velocity, which is the green curve. Therefore, in the compaction experiments, it was okay to use the 2D velocity to predict the compaction boundaries. For the particle patch system, comparing the experimental images with the velocity plots near the wall and at the center line qualitatively confirms the three-dimensional flow effect. If you pair the solid and dotted lines with the same color and focus on the difference of the two velocities, you can see that it qualitatively tells you the width information of the particle patch. The trend of the patch size agrees well with the flow velocity distribution in different pores. From this analysis, we can conclude that it is primarily the diffusiophoretic velocity that translates the particle patch, and it is the diffusiosmotically induced liquid flow that disperses the patch to the widths corresponding to the local flow velocity. We noted that such a configuration is similar to the flow-driven dispersion problem in a pipe flow. The only difference is that in the pipe flow, the patch translates and disperses by the imposed flow velocity, whereas in our system, the patch translates at the diffusiophoretic velocity and disperses by the flow velocity. Using the analogy between our dead-end pore and the pipe flow systems, we were able to apply the Taylor dispersion idea with the listed assumptions, and we were able to reduce the three-dimensional transport equation to a one-dimensional equation. This is done by taking the area average of the equations and considering the symmetry of the three-dimensional flow structure. As a result, we obtain the effective diffusivity of the particle patch that includes both the particle's own diffusivity and the influence of the three-dimensional flow velocity, which is of course closely related to the wall diffusiosmotic velocity. To validate our Taylor dispersion analogy, we designed a new set of experiments with a long pore. To remain within the regime where the Taylor dispersion concept applies, we selected a pore length large enough such that the typical timescale for a particle to translate to the pore end is much greater than the typical timescale for it to diffuse across the pore. For 0.5 micron carboxylate modified polystyrene particles in a sodium chloride gradient, we were able to predict the diffusiophoretic translation and diffusiosmotic dispersion pretty well. Only by including the three-dimensional flow velocity can a correct particle distribution be obtained in the one-dimensional diffusiophoresis experiments in a three-dimensional pore. We also confirmed that our one-dimensional model with effective diffusivities predicts well the behavior of particles of different sizes or different diffusivities. Finally, we directly compare the 1, 2, and 3-dimensional models without any dispersion with 2 and 3-dimensional dispersions. For the systems where three-dimensional effects are not averaged out along 1 or 2 dimensions, full consideration of the three-dimensional flow effect is necessary because we are never free of the diffusiosmotically induced liquid flow in the experimental systems designed for diffusiophoresis. To conclude, we investigated a dead-end pore system where three-dimensional flow effects are not negligible in the analysis of particle diffusiophoresis. To unravel the three-dimensional information in one-dimensional diffusiophoresis experiments, we focused on the analogy between our system and the Taylor dispersion configuration. By applying the Taylor dispersion idea, we were able to reduce the 3D transport equation to the one-dimensional equation with an effective diffusivity, and it was further compared with long pore experiments. We suggest that knowing 3D flow structure is important for identifying correct particle distributions in dead-end pore experiments of diffusiophoresis and also in other geometries. Please read our published article for more details of the model derivation and the experiments. Thank you for watching this video, and please feel free to reach out to me or any of the co-authors if you have any questions about this work. In this video, I'll discuss my recent paper, Diffusiophoresis in the presence of a pH gradient. The work is original and it's part of the special collection Interfacial Active Matter in Physical Review Fluids. It was published in November 2022. The main theme of the study is diffusiophoresis in the presence of pH gradients. We used a microfluidic dead-end pore geometry and synthetic microspheres to investigate the influence of pH change on the particle behavior. To test different signs of the zeta potential, polystyrene and amine-modified polystyrene particles are used. The pH-dependent zeta potential was included in the theoretical model by considering the charge regulation idea. We also noted that the pH gradient changed the surface potential of channel walls and affected the diffusiosmotically induced liquid flow. Now let's look into the details. Diffusiophoresis is the spontaneous motion of colloidal particles under a solute concentration gradient. If a spherical particle with a negative surface potential is located under a simple salt gradient, diffusiosmotic flow is generated along the particle surface down the gradient. Since the particle is mobile, the shear stress will make it move to the opposite direction, and this motion is called diffusiophoresis. The simplest form of the diffusiophoretic velocity formula is the mobility times grad log c. Here, gamma p is the diffusiophoretic mobility that is a function of zeta potential, and c is the concentration of salt. For detailed explanation of diffusiophoresis, please refer to the inserted video on the top right corner. Having diffusiophoresis is considered advantageous for moving micron-sized particles, as the typical particle mobility induced by a simple salt gradient like sodium chloride is 1,000 times higher than the particle's own Stokes-Einstein diffusivity. In this work, we focus on the effect of varying zeta potential on diffusiophoresis. The zeta potential of a surface is a result of complex interaction between the surface and the ions nearby, and the pH of the surrounding liquid is one of the parameters that strongly influence the zeta potential of a surface. By utilizing the dead-end pore geometry, we observe the particle motion along transient pH gradients of various range. Along the narrow pores connected to one side wall of the main channel, a one-dimensional solute gradient can be created. Depending on the initial and boundary conditions, we can entrain particles into the initially empty pore, compact existing particles toward the end of the pore, or move a patch of particles along the solute gradient. One very important feature of the dead-end pore system is that the solute gradient that moves particles also generates the diffusiosmotic flow along the pore walls. This surface flow induces bulk liquid flow inside a pore, and as a result, the apparent particle velocity becomes the sum of the diffusiophoretic velocity and the local flow velocity. I won't go through the details of the liquid flow here, and I'll move on to the pH dependence of diffusiophoresis. Now let's consider the simplest acid and base, hydrogen chloride and sodium hydroxide, and the corresponding diffusiophoretic mobilities at different zeta potential values. For hydrogen chloride, the mobility is positive for positive zeta potentials, whereas for sodium hydroxide, the mobility is positive for negative zeta potentials. Therefore, if we put the negatively charged polystyrene particles under a sodium hydroxide gradient, the particles move up the gradient. We also confirmed that the positively charged amine-modified polystyrene particles move up the gradient of HCl. So far, the sign of the mobility seems to be consistent with the experimental observation. However, if we put the amine-modified polystyrene particles under a positive NaOH gradient, the particles behave similarly to the negatively charged polystyrene particles. We asked if this may be due to the pH-dependent zeta potential of the APS particles, and the zeta potentiometry partially confirmed the question. Between pH 11 and 12, there is sudden sign change of the zeta potential of APS particles, and these pH values are consistent with our test condition. Before we fully analyzed the results from the current setup, we conducted a separate set of experiments examining the diffusiophoretic behavior of APS particles in a wide range of pH gradients. As there is a sign change in the zeta potential of amine-modified polystyrene particles, we designed a new set of experiments to observe the behavior of these particles initially immersed in a 10 millimolar HCl solution and then exposed to concentration gradients created by 1, 3, 5, and 10 millimolar sodium hydroxide. To highlight the front of the particle trajectories while using a finite number of particles, we chose the particle patch configuration. Let's now focus on the behavior of the particle front. When there is 1 millimolar NaOH in the main channel, the APS particles are always positively charged and the direction of motion is always down the pH gradient toward high HCl concentration region. When there is a 10 millimolar NaOH solution in the main channel, the APS particles are initially positively charged but become negatively charged as interdiffusion occurs between NaOH and HCl. Consequently, the particle front changes its direction of motion around halfway along the pore. For the cases with 3 and 5 millimolar sodium hydroxide, the flat particle fronts stop moving near 600 micrometers and then become a parabolic shape. Along with the travel distance, the shape of the particle front is an important feature to point out. In all 4 experiments, the particle front is flat when traveling toward that end. This indicates that the PDMS wall is almost uncharged in the presence of 2 millimolar HCl, and there is no diffusiosmotic flow along the pore walls. We choose this regime where the flat particle front is moving down the pH gradient and analyze the trajectories with a theoretical model. To accurately predict the particle front behavior in the patch experiment, we used the multi-ion diffusiophoresis model with a pH-dependent zeta potential. The charge neutrality and the zero current conditions hold, and the formula for the diffusiophoretic velocity now includes interactions among all ions and the zeta potential of the particle surface. We consider the charge regulation model for the pH-dependent zeta potential. For commercial polystyrene particles, their surface is often treated with sulfate, carboxylate, or amine groups. Since the extent of proton binding to these functional groups at different pH directly affects the surface charge density, we can calculate it by considering the acid-base reaction kinetics and the Boltzmann distribution of ions. For the amine-modified polystyrene particles used in this project, the surface has both the sulfate and amine groups. So, by using the number density of these groups and the pKb value as the feeding parameters, we can get a nice curve that represents the pH-dependent zeta potential of the APS particles. For direct comparison between the experiments and model, we measured the particle front trajectories from the chymographs and calculated the one-dimensional trajectories using the matching initial position of the particles. Such a one-dimensional calculation is sufficient for this comparison because the particle front is flat and there is no influence of the diffusiosmotically induced flow. By using the pH-dependent zeta potential obtained from the previous slide, the particle front trajectories were accurately predicted without additional fitting parameters. This comparison indeed confirms the pH dependence in the diffusiophoresis of APS particles. Now, knowing the sign change behavior in the zeta potential of APS particles between pH 11 and 12, and knowing the occurrence of the pH-dependent diffusiophoresis, we are back to our initial experiment. Is it enough to explain the behavior of APS particles under this NaOH gradient in the compaction configuration? Since the compaction boundary is not flat but parabolic, we must think about the influence of the wall diffusiosmosis before reaching a conclusion. To test different combinations of the influences of wall diffusiosmosis and APS diffusiophoresis, we designed another set of experiments testing various pH gradients created above pH 7. We chose the combinations of sodium chloride and sodium hydroxide and controlled the ionic strengths to be 2 millimolar in the main channel and initially 20 millimolar in the pore. As a result, the APS particles are always positively charged in the condition 1 and always negatively charged in the condition 4. The surface potential changes its sign in the conditions 2 and 3. As shown in the pictures, we observed different compaction behaviors of the particles that were initially filling the pores. The main feature to remember in these experiments is that the APS particles moved up the gradient in all 4 conditions, regardless of the pH-dependent sign change of the zeta potentials. Similar to the earlier particle patch experiments, we tried to predict the directionality using the pH-dependent zeta potential and the one-dimensional particle trajectory. However, this calculation failed to predict the compaction behaviors of the APS particles. Unlike the particle patch experiment where the front shape was flat, the compaction boundaries in the current experiment are all parabolic. This means that the influence of the wall diffusiosmosis-driven flow is not negligible, and we must include the flow effect in calculating the particle trajectories. To accurately include the effect of diffusiosmotic velocity, we consider the pH-dependent zeta potential of PDMS walls. The correct comparison is now shown in the new plot. Only after setting the particle velocity as the sum of the pH-dependent diffusiophoretic velocity and the local flow velocity, the direction and magnitude of the transport is accurately predicted. Therefore, it turns out that the very initial experiment where the APS particles compacted along the positive gradient of sodium hydroxide is an outcome of the combined pH-dependent zeta potential, multi-ion diffusiophoresis, and the diffusiosmotically induced liquid flow inside the pore. Finally, we conduct a thought experiment or a numerical experiment by considering the particles with different isoelectric points. These 3 curves represent 3 different particles with different zeta potential functions of pH. If these particles are put under a concentration gradient of sodium chloride, the diffusiophoretic trajectories will look like the solid lines, and the trajectories that include both the effects of diffusiophoresis and diffusiosmotically induced liquid flow inside a pore will look like the dotted lines. Since the sodium chloride solution is pH 7, we focus on the particle with the isoelectric point 7. This particle will be always uncharged in the sodium chloride solution, meaning that the diffusiophoretic velocity is 0. However, the dotted line tells us that if the pore wall is negatively charged, the particle can still move into the pore by the diffusiosmotically induced liquid flow, and the typical velocity scale of this advection will be the same as the typical diffusiophoretic velocity set by the same salt gradient and the same zeta potential. Therefore, we suggest that it is important to correctly estimate the diffusiophoretic transport and diffusiosmotically induced liquid flow, as we are never free of the wall diffusiosmosis in an experimental system designed for diffusiophoresis, and the pH-dependent zeta potential is a common feature of such system elements. In my previous video clipped on the top right corner, I had discussed the 3-dimensional flow effect inside a dead-end pore geometry. And in the current study, I investigated the pH-dependent diffusiophoresis both in the absence and presence of the diffusiosmotically induced liquid flow. By doing so, I tried to demonstrate the complex nature of diffusiophoresis as a physicochemical hydrodynamic phenomenon. Before concluding the video, I would like to leave a remark about this feature of diffusiophoresis. Diffusiophoresis is motion of particles relative to the surrounding liquid, and it is induced by the generation of a surface flow. Scientists are actively investigating the phenomenon by focusing on various particle types and various flow configurations with both theoretical and experimental approaches. No matter what particle is used and no matter how the flow condition is set up in the project, the very fundamental aspect of diffusiophoresis, which is the surface flow-driven phenomenon in the presence of flow, must be carried along in the research. In this way, we can avoid misclaiming any apparent enhanced motion as diffusiophoresis, and we can prevent confusing fellow scientists and general audiences with false information. To conclude, we investigated diffusiophoresis of synthetic microspheres under various pH gradients experimentally and theoretically. The apparent behaviors of APS particles tell us that the directional motion of a particle under a pH gradient can be a combined result of pH-dependent diffusiophoresis and diffusio-osmotically induced liquid flow. Again, as diffusiophoresis is a physicochemical hydrodynamic phenomenon, it is important to ensure that this fundamental aspect is not overlooked when tracking particle motion. Thank you for watching this video, and please let me know if you have any questions about this study. In this presentation, I'll introduce my latest publication, Motorless Transport of Microtubules Along Tubulin, RanGTP, and Salt Gradients. It was published in Nature Communications on November 1st, 2024. The main idea of this work is about identifying diffusiophoretic transport of stable microtubules along cytoplasmic and higher concentration gradients of soluble tubulin, RanGTP, and magnesium salts. The motorless motion of intracellular macromolecules along various concentration gradients of smaller species is a popular research question in biology and biophysics. Such a transport phenomenon is called diffusiophoresis in colloid science. We focus on the fundamental aspect of diffusiophoresis as a physicochemical hydrodynamic phenomenon and take a step-by-step approach to validate the observed behavior of microtubules as diffusiophoresis. Now let's look into the details. Microtubules are dynamic filaments that form spindles in eukaryotic cells during mitosis and meiosis. It has a cylindrical shape with a 25 nanometer outer diameter, and its length can vary up to tens of micrometers depending on the intracellular location and the stages of cell cycles. Among many species present in cytoplasm, it is well known that the RanGTP gradient is a critical regulator of spindle assembly and positioning in both mitosis and meiosis. Also, it was recently visualized that there is pre-accumulation of tubulin molecules near the nucleation sites of spindles. Given the concentration gradients of relevant species and the transport of microtubule segments in spindles, we asked if diffusiophoresis of microtubules can be present during spindle assembly. Diffusiophoresis is the spontaneous motion of particles along a concentration gradient of solutes. Validating the occurrence of diffusiophoresis in spindles is not as simple as it sounds. Diffusiophoresis is a physicochemical hydrodynamic phenomenon driven by the osmotic flow generated along the particle surface within nanometers of interaction length scale. If a negatively charged particle is put under a simple salt gradient, diffusioosmotic flow is generated along the particle surface. As the particle is mobile, the shear stress will make it move to the opposite direction, and this motion is called diffusiophoresis. Therefore, when analyzing the particle transport in such a configuration, it is necessary to identify the coupled interactions among particles, solutes, and the fluid flow. All experiments in this project were conducted in a microfluidic channel with a dead-end pore geometry. By using different initial and boundary conditions, we either entrained microtubules into initially empty pores or compacted existing microtubules along various concentration gradients of solutes. In this way, we can set up a one-dimensional concentration gradient of solutes and observe the response of stable microtubules that are approximately 10 micrometers long. Among many solutes that potentially influence the behavior of microtubules, we thought the most important one to investigate is the soluble tubulin. Inside a cell, microtubule generation requires that the concentration of tubulin near nucleation sites be above a critical level. Therefore, near microtubule structures, it is natural that a concentration gradient of soluble tubulin is present. We used 2 different buffers as surrounding media and observed entrainment of stable microtubules down the gradients of micromolar tubulin. At this point, we cannot yet state that the motion of microtubules is diffusiophoresis, but we notice a few important features from this set of experiments. First, the entrainment distance of microtubules depends on the tubulin concentration gradients. Second, the buffer type affects the microtubule transport. Lastly, the entrainment fronts in all experiments have a parabolic shape, meaning that there can be the influence of the slip flow generated along the wall in the presence of the tubulin gradients. Before analyzing the phoretic behavior of microtubules, we must rule out the effect of liquid flow generated inside the pore. The parabolic entrainment front indicates that the imposed tubulin concentration gradient induces osmotic flow along the pore walls, making the flow velocity inside the pore non-uniform. The rescaled flow velocity can be plotted versus distance across the pore, and we can detect a Y position where the flow velocity becomes 0. This means that if we track the microtubule entrainment front along y equals 40 micrometers at each time point, we are detecting purely the phoretic component of the apparent microtubule motion. The graphs show clear concentration dependence of microtubule entrainment. Since we only visualize the effect of tubulin concentration gradient on the apparent travel distance of microtubules, we must further identify all the interactions listed here to fully validate the diffusiophoretic mechanism underlying the observed microtubule migration. We take a step-by-step approach to separately identify the interactions between microtubules and background species, interaction between tubulin and background species, and finally, the interaction between microtubules and tubulin molecules in the presence of the background species. We next conducted 2 sets of experiments using magnesium chloride gradients in BRB80 buffer. In the first set, we observed the response of microtubules under magnesium chloride gradients, and in the second set, we observed the behavior of commercial polystyrene microspheres. Both the microtubules and polystyrene particles move up the gradient of magnesium chloride. The behavior of polystyrene particles is straightforward as it can be directly analyzed with an electrolyte-driven diffusiophoresis and diffusioosmosis model. Therefore, the configurational analogy between the 2 sets of experiments can tell us more about the magnesium chloride-driven migration of microtubules. We plotted the entrainment distances of microtubules measured along y equals 40 micrometers for 6 different magnesium chloride concentration gradients. As shown in the linear plots, the entrainment behavior of microtubules indicates diffusive nature of this transport process. For the magnesium chloride experiments, we analyzed 2-dimensional entrainment profiles by detecting the particle front at 5 different Y positions. In all experiments, microtubules migrated fastest along the center line and slowest near the wall, making the front shape parabolic. To validate a diffusiophoretic mechanism for the microtubule behaviors along magnesium chloride gradients, we used a multi-ion diffusiophoresis and diffusioosmosis model. The model considers coupled transport of all electrolytes in the liquid phase and the diffusiosmotically induced liquid flow inside the pores. Particle trajectories along different Y positions were obtained by considering local flow velocities at the corresponding Y positions. The measured and calculated trajectories are compared directly by using the zeta potentials of the microtubules and the pore walls as fitting parameters. For 25 millimolar magnesium chloride, we obtained the best fit with the wall and microtubule zeta potentials of -7.2 and -35.5 millivolts respectively, which are consistent with the previously reported zeta potential values. Therefore, with this comparison, we confirm that the magnesium chloride gradient-driven migration of microtubule is diffusiophoresis. Comparison between the model and experiment was done for all magnesium chloride concentrations, and we conclude that microtubules can undergo diffusiophoresis in the presence of magnesium chloride gradients in BRB80 buffer. The main parameter for the surface interaction between the ions and microtubules here is the negative zeta potential of microtubules. We also confirmed that magnesium chloride-driven diffusiophoresis of microtubules and polystyrene particles occurs similarly in the CSFXB buffer with different magnitudes of the fitting parameters and the entrainment distances. We now move on to the next part, identifying the interactions between tubulin and background species. We examined the diffusion behavior of soluble tubulin separately using 5 different background solutions without any microtubules present. We observed that tubulin diffusion is largely unaffected by the background species, and the measured diffusivity of soluble tubulin is approximately 10 to the minus 10 meters square per second, consistent with the known size of the alpha-beta tubulin dimer. The results suggest that when analyzing the tubulin gradient-driven migration of microtubules, we're allowed to consider only the diffusion of tubulin without accounting for the coupled transport of the background species. Finally, we're almost set to better understand the details about tubulin-driven transport of microtubules. Before returning to the microtubule results, we conducted a set of experiments with polystyrene particles under micromolar gradients of soluble tubulin. Analogous to the microtubules, polystyrene particles migrated down the tubulin gradients. We applied the non-electrolyte diffusiophoresis model to analyze tubulin-driven migration of polystyrene particles, and compared the model and experiments by setting the interaction length scale as the fitting parameter. The 100 nanometer interaction length scale was larger at lower tubulin concentrations, indicating that tubulin molecules are more widely spaced under these conditions. We considered the repulsive interaction between tubulin and polystyrene particles, which is consistent with the negative surface charges of both. Since the analogy between microtubules and polystyrene particles holds due to their negative surface potentials and micrometer size, we can apply the same non-electrolyte diffusiophoresis model to the microtubule experiments and examine whether the interaction length scale is also consistent. The obtained values for the interaction length scales in the microtubule experiments were also around the 100 nanometers. The scale and trend matched the average separation distance in micromolar tubulin solutions, making our step-by-step validation and conclusion about microtubule diffusiophoresis physically reasonable. We suggest that there is a long-range interaction between microtubules and soluble tubulin due to their negative surface potentials, and that this interaction is weaker in BRB80 buffer compared to CSFXB, resulting in a smaller diffusiophoretic travel distance. Our surface potential argument as the main source of the long-range interaction is further validated using amine-modified polystyrene particles which have a positive surface potential. We confirmed that the amine-modified polystyrene particles migrate up the tubulin gradient, opposite to the migration direction of microtubules and carboxylate-modified polystyrene particles. So far, we have identified the diffusiophoresis mechanism for microtubules in the presence of tubulin and magnesium chloride gradients within buffer environments. In the next part, we present experiments with other solutes and medium to show that diffusiophoresis of microtubules can be present in the cytoplasmic environment as a motorless transport mechanism. Another important protein gradient that arises during spindle assembly in addition to tubulin is RanGTP. It is known that the RanGTP gradient is a critical regulator of spindle assembly and positioning, so it is necessary that we identify possibility of RanGTP-driven diffusiophoresis of microtubules. We first tested both directions of RanGTP concentration gradients and observed the response of microtubules. Unlike the previous experiments, it appeared that the microtubules move both up and down the gradients of RanGTP in CSFXB buffer, with little concentration dependence and smaller travel distances. To understand this two-direction behavior of RanGTP-driven transport, we investigated further details of the entrainment setup and observed that there is depolymerized tubulin with fluorescent signals diffusing in the background. Therefore, we investigated the cross-diffusion behavior of tubulin and RanGTP separately and found out that the tubulin diffusion was enhanced at higher RanGTP concentration gradients. It must be that in the microtubule experiments with RanGTP, the generation and diffusion of the depolymerized tubulin is never negligible and is always affecting the diffusiophoretic behavior of microtubules. To rule out the microtubule depolymerization, we use polystyrene particles and examine the directionality of RanGTP-driven diffusiophoresis of negatively charged particles. Without any background tubulin, the negatively charged particles always migrated down the gradients of RanGTP, and only in the presence of the cross-diffusion of tubulin and RanGTP in the background, the particles migrated up the RanGTP gradient. This is why the microtubule diffusiophoresis show the two-direction behavior and little concentration dependence along the RanGTP gradients. In the published work, we also included the model predictions for the RanGTP-driven diffusiophoresis of microtubules, and we concluded that microtubules can undergo diffusiophoresis along various relevant solutes of spindle assembly. Finally, we reproduced the diffusiophoresis of negatively charged particles in an active cytoplasmic environment using the Xenobus laevis egg extract. Polystyrene microsphere was chosen as a representative negatively charged particle to rule out other physiological processes that could occur with microtubules. We confirmed that magnesium chloride, tubulin, and RanGTP-driven diffusiophoresis occur even in the frog egg extract condition, which lead to our final conclusion that microtubule diffusiophoresis can be present during spindle assembly. More details of this work can be found in the published article. Thank you for watching this video, and please let me know if you have any questions.